Linear equations. Everybody's going to raise their hand, right? What does it mean by a system of linear equations? What's the simplest way you could say system? What do I mean by a system?
More than one.
More than one. That's all it means. It means more than one. How many of you at some point in some way have worked with more than one linear equation at the same time? We've done that in this class before, even though we haven't specifically labeled it as such. Well, I think I've actually said the phrase. So this shouldn't be so totally new. So totally new. We're going to be solving systems of linear equations, and there are 3 general methods we'll be focusing on. 3 words. What's one word for one of the methods? If you had to describe the first method of what we're going to use for solving linear equations, systems of linear equations, there's one method that we'll try first. Anybody want to know what that? Anybody know what that's called? So let's read 4.1 last time. What's it called? Something with an ing. It's what?
Checking.
We're going to check our answers. True.
Solving.
We're going to be solving the solutions using what method? Good. What? What? Graphing. So one method we're going to use is graphing. Essentially, make a picture and use the picture to find a solution. Anybody remember what the second method is called? Mark?
Substitution.
Substitution. And there's a third one. Begins with an E. Anybody else? Mar, I know. Anybody else plays Mar? Anybody remember what it's called? Hannah? Yeah, elimination. If you ever used a different textbook or a different class, sometimes they call it linear combination method, but elimination is what this book calls it. Graphing. What do they mean by graphing? Well, first of all, let's talk about what a graph is. What a graph is. So this graph had this expression, this visual expression has 2 graphs on it. One of them is number in millions of dollars of sales of digital cameras in the year since 2000. Can someone give me a general piece of information? What can you conclude about the sales of digital cameras over time in the past 13 years of digital cameras? Alex? Be simple and direct. You don't have to give me a number, but what can you tell me about the sale of digital cameras over the past 10 years?
Somewhere in the 2001.
No, I want more general. What can you tell me about that line? Just tell me. What can you tell me about that blue line? Milo. It's going up. It's going up. And what's happening to the red line, which is digital camcorders? It's going down. Right, exactly. First thing you have to do is understand what a graph is. What is the graph of a linear equation? So theoretically, could we write the equation of either of those lines? Theoretically. They look like lines, correct? So let's say this one was, we'll call it, I don't know, h of x. H of x is something. That graph, what does the graph represent? If h of x was known, that's going to be negative something plus something, right? Something x plus something. What does the graph represent, Alex?
Function of x.
The graph is the picture of what? Yes, it is the function, but it's the visualization of what? Each point represents a what?
Solution.
Yes. So the graph is the collection of
Solution.
what?
Solutions.
All solutions. The graph is the collection of all solutions. It's the collection of all solutions. So the blue line is the collection of all solutions to that linear equation. The red line is the visualization of the collection of all solutions to the red one. Which point are we spending our time trying to find? What are we going to be spending our time finding when we're solving a system of linear equations? On that graph, which one are we looking for, Mar?
The point that satisfies both.
Yes, exactly. So which point? How do you express that out loud? The intersection. We are going to spend our time looking for the intersection, because that point is on both graphs. And if you have one set and another set, the point where both sets exist is a solution to
The system?
yes, both or all equations in the system. Yes, Mark.
What does the intersection, that point, mean in terms of like the sales?
It just means that at that specific time, the exact same amount in millions of dollars was being sold in each type of camera. That's a good question. What does it mean? Absolutely. It means at that specific instance, a better way to say it, judging by this whole picture, would be at that point in time, that's when more digital cameras started being sold than camcorders. But at that specific instant, the same number of dollars, right? There are certain inflection points like this that happen all the time. When a new technology is introduced that ends up overtaking another one, it's really interesting to be able to predict. Like you'll have a line that's going like this, something is falling and something is growing. So it's really helpful to know when they're going to pass each other. Can anybody come up with an example of something that something with regards to media or technology that has decreased in sales or activity or use and another thing that's overtaken it? Yeah, Connor. Like a Walkman, yeah, exactly, Walkman, and then overtaken by like an MP3 player. I got my first MP3 player in 1999. I bought a Rio 32. What do you think the 32 stood for? Not even. It was a Rio 32 megabyte. Cost me just under $300. But it was unbelievable because I could plug it into my computer and immediately move something over and then unplug it and listen to it immediately. That was totally different than how it used to work. When I was in high school, the best way to get songs was to wait till Sundays or the end of the year, the end of the month, when they played like the top 100 songs on the radio. And like you'd be doing your homework and you'd spend the day hitting record every time your favorite song came on. And then you'd carry that tape. That was your mixtape for like the month, right? And then all of a sudden, 20 of us were on the internet. You can suddenly find MP3s, and then like iTunes was debuted like 4 years later. Totally changed, but those things overtook. Any other examples of technologies that have overtaken old technologies?
TV and radio.
Kind of, yeah, but more directly. What do you carry around right now? All of you are probably carrying something around. Yeah. So, for example, 25% of households in the United States right now only have a cell phone. So right now, 75% have a landline. So what's going to happen probably sometime in the future? Well, landline keep going down. Cell phone usage goes up, and at a certain point, households will only the same number of households will only have a cell phone. There are 7 billion people in the world. How many of them have access to a cell phone? 5 billion. 7 billion people in the world, 5 billion of them have access to a cell phone. That's pretty interesting for a lot of different reasons. One, that's a lot of people, right? I'm not saying each person has a cell phone, but a family might have one. That counts as access for the whole family. That's particularly interesting because that's way more people than have access to clean water in the world. Put that out there, yeah. So we're interested in finding intersection points. We're interested in finding intersection points. The first thing we have to do is figure out how to decide whether a set of points is a solution to both. How do you figure out if ordered pairs are a solution to both? Yeah.
Just plug them in for each.
Plug them into both. Exactly, right. So here's an example right here. So let's say I gave you this system and made it really impossible to read. Ooh, and really, really hard to read. Let's see if I can mess this up even more. I definitely clicked on, why does it allow me to do that? I don't know. Here's a system for you, and there's the point. By yourself, do not say this out loud, tell me if that point is a solution to that system. Some notation that you generally see in other books. Usually when it's a system of equations, you see one bracket written like this. There's no closed bracket on the other side, but what does that bracket kind of signify? Like a linkage, exactly. They're tied together, both need to be true. You generally see that in other books. Okay, so let's say you had one of these linear systems. Let's say we had this linear system right here. Let's just say we had this one. So we had x plus, well, I clipped that wrong. Let's say you had x plus y equals 6 and 4x minus y is 14. Let's say we had that right there, okay? Do this for me right now. I would like you to graph both of those lines on the same set of axes. Can someone, so you graph this, you know, you got 0, 6 and 6, 0, 0, 6 and 6, 0, and then you ended up with something like this maybe, and then you estimate that point, and you hope it comes out to 4, 2. We know the answer is 4, 2. What's one limitation to graphing, though, that you've now figured out? What's one limitation?
It has to be in standard form.
It doesn't have to be in standard form. You can graph any form of the line you want, but in finding Aubrey, Harrison, in finding solutions, in finding where they intersect, what's one limitation you've run into? How pretty are your pictures?
So pretty.
They're so pretty. Are they always perfect? No. They're not always perfect. For example, could the intersection be some weird fraction?
Yeah.
Yeah. And is that going to be easy or hard to figure out on an intersection value? Like if the answer was 1 1/7, comma 16 19ths, would that be easy or hard to see on your graph?
Hard.
That would be hard to see on your graph. So one limitation to graphing, it is not exact. Does it give you a general idea? Sure. And sometimes it will give you, you'll get an answer and then you check it and it works. Sometimes will it work perfectly? Sometimes will it work perfectly?
Oh, yes.
Yes. Sometimes it will work perfectly, but it's quite frequently the case that it won't give you an exact answer because maybe the intercepts are, like, it's really hard to estimate like 1/7, for example. It's really hard to estimate a third, and sometimes fractions are really hard to graph, but does it give you a general idea of where the solution is? A general idea? Yes. You know, it would help if it was 4, 2 instead of 4, 2.8, or 2.679, right? Okay, so you can graph them. Let's try this again. The people that were seated, can you go up to the... Let's just do this out together. What are the two intercepts for the first one? Can someone raise their hand and tell me them? What are they? First one, OBS. Intercepts are points. Give them to me as 2 points. What are they? 5 is not a point. Give me one of the intercepts as a coordinate. 5, 5 is not an intercept. 5, 0 is an intercept, and correct. So when we graph those two, well, let's find the intercepts first. What are the intercepts for the second one, Milo? For this one, -4. 0, -4, and
-4, 0.
Nope. How did he get 0, -4? He plugged in 0 for x. 0 minus y is equal to 4. So y has to be -4. There you go. So there it is. So the intercepts, what's this one going to be? 0 what? 0.
-4.
And what's the other intercept, Milo? And 2 times what is 4? 2. 2, 0. So now you know where the intercepts are. So what do you do with those points? You graph those points, and then what do you do once you graph those points? Exactly. So we have 5, 0. Let's say it's up there. It's got 0, 5, and 5, 0. So that's 5 and 5. What do you do once you have those two?
Graph the line.
Yes. So we have that one. And then, bless you or excuse you or something like that. 0, -4 is going to be right about there. And 2, 0 is going to be right about there. So what do you do with those two?
Graph the line.
Graph the line. Thank you. So we graph this line. And then what point are we interested in? What point are we really interested in? We're interested in, well, we're interested in that intersection. What is that? And maybe it's 3, 2. Yeah. So what can you do to see if that's true? Is that, what can you do? What's the one word you can do? You can?
Evaluate.
One word. Evaluate. Where?
The system.
Yeah, at 3, 2. You can check that. Is 3 plus 2 equal to 5? Yes, so the first one checks. What about 2 times 3 minus 2? That's 6 minus 2, which is 4. So does it check? Yes. So where does it actually intersect? 3, 2. But what did we notice about graphing? Is it exact? No, it's not exact. It's not exact. So there are other methods, but here is what we're going to be dealing with in terms of numbers of solutions. First, there's 3 numbers of solutions, and it's similar. This is exactly what I've said before. If 2 lines intersect, how many times can they intersect? At most. Well, once. Or if they're parallel, do they intersect? So there's going to be no solutions. But then if they're the same line, how many intersection points does it have? So the number of solutions, 1 solution, no solutions, or infinite number of solutions. Those are the 3 types of quantities of solutions we could have. So graphing is our first method, but we need other methods. We'd like methods that are not as inaccurate. We would love methods that are accurate. Perfect. We love methods that would give us exact answers. So we're going to solve linear systems by substitution. How many people have done by substitution before?
Substitution is fun.
Substitution is fun. So what's the first? So if I asked you to solve this system right here with substitution, what's the first thing you would need to do? Does anybody remember if you're going to solve a system by substitution? Summer, what's the first thing you do? Not specifically with this one, but what's the first step you take given a system? You pick one of the variables and solve for it. What's nice about this system? So solve for one of the variables in one of the equations. Well, what's nice? It's already solved. Once you've solved for a variable, then what do you do? Once you've solved for one of the variables, which we have, x in a second, what do you do next? Mar? Substitute, yeah. You sub. And where's this one going to go? Where do you plug x equals y plus 2?
2x.
Into the x in 2x. So solve, sub, and then you... I'm going to show you. Watch. We know x is equal to y plus 2, correct?
Yeah.
Well, we know 2x minus y is equal to 6. So instead of x, what am I going to write? Instead of x, what am I going to write, Nick? We know x is equal to y plus 2, so where are we going to plug that in? Exactly, y plus 2. Why did we do that? Can someone tell me why we did that? Alex.
So we can get y in terms of x.
Well, we have no x anymore. Hold on. In that black box, do you see an x?
No.
We did that so that we could get rid of the x. We now have one equation in one variable, which means we can solve for y. We can solve for y. One word for what's the next step on to solve this. One word. What do I do? No. Yes, we're going to solve. One word for what we're going to do next. Distribute. 2y plus 4 minus y is equal to 6. What should I do next? Yep.
Add the
Combine like terms. We have 2y and minus y. How many y's do we have? So we have y plus 4 is equal to, so what does y equal? 2. Once you have y equals 2, we need to get x. How do we get x? Oh, look, x equals y plus 2, and we know y is equal to 2. So x is equal to 4. So we think x is equal to 4. What's the last thing you should always do? Check your answer. So we think the answer is the 0.42. Can we check that up here? Where's the system? Yeah. 2x minus y. 2 times 2. Sorry, what was x going to be again? 4. 2 times 4 minus 2. That's 8 minus 2. What is that? Everybody, hands up. 8 minus 2. What is it? 6. So does it check? Yes, it does. What about 4 equals 2 plus 2? Is that correct? Yes, it is. So does this work?
Yes.
It does check. It does check. Check your answer. Check it. Check it. Check it. Yes, absolutely. You will get a point off on every question that you don't check where I say check. Absolutely. Even if it's correct. So what are you going to do? You're going to solve one of the equations for either variable. Theoretically, you have two equations with two variables, so you have 4 possibilities. Usually one option is the easiest. In this case, was one option the easiest? Yeah, it was already solved for you. X equaled what? So you didn't have to do it. It was already solved for you. So after you solve one of the equations for either variable, you then substitute, solve, find the other value, and then check. Check, 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 check. Absolutely. Okay, the first people who are at the board, please go to the board now. Solve that system for me. Everybody else, do that on your own for an answer. I'm seeing 1, 5, 1, 5. What'd you get over there? Who did the blue work over there? Oh, that's nice. She did something. Who did the blue work?
I did.
Hannah. What did you do over there that no one else did? Check your work. Good job. Did you check your work too? Who checked their work? Be honest here. Who checked it?
Sit down once I got
That's true. That is true. I did tell you to sit down. That is true. But 1, 5. Now, what's nice about this is if you do this and check your work, are you pretty sure your answer is correct? If you graph, you can kind of get an estimate and then check it and then maybe guess again. This is just another method. Is this probably the most common method you're going to use in your math career? Yeah. But there are other methods. Sometimes the algebra is really hard, but you can graph, and you're just interested in an estimate. So is graphing a good way to get a quick estimate? Yeah. Algebra gives you an exact. Okay. So let's move on a little bit before. Maybe. 1, maybe-ish. Here's the basic idea to elimination, Harrison. If A equals B and C equals D, you can add the equations together. So if A equals B and C equals D, A plus C is equal to B plus D. If you have two statements like that's really nice. Why? It's nice because you might get a system like this. Take a look at this, everybody. Put your pens down. Take a look. Just drop. Take a look. You have 2x plus 3y equals negative 6, and you have 4x minus 3y equals 6. You can add equations together. Look what happens. You have 2x plus 4x plus 3y minus 3y is equal to negative 6 plus 6. All I did, look what I did. All I did was add both sides together. You don't even have to have the parentheses in it. That was just me being overly neat. You have 2x and 4x. That went right here. And you have 3y and negative 3y. That went right here. What's 2x plus 4x, Mar? Nick, what's 3y minus 3y?
0.
What's negative 6 plus 6, Alex Faye?
0.
So what does x equal?
0.
Hey, now x equals 0. Can we solve for y? Yeah, we know in the first equation. Well, no, we don't need to. Look, we just plug it in. We know that 2x plus 3y is equal to negative 6. What do we plug in for x? It's right there. What do we plug in for x? 0. So we have positive 3y is equal to negative 6. What does y equal? Negative 2. What was the magical thing here that made it possible for us to do it this quickly? What was the magical thing that you had, Alex? Or yeah.
A plus B equals B plus C.
We had two equations, but what was the magical thing that was a thing that was in the equations that made this nice? What was the nice thing, Nick?
So doing this finds the intersection.
That's what we just did. We just found the intersection. That's correct. So I'm asking the question again. What was the nice thing about these equations? Mar.
Yeah, the opposite coefficient.
You had opposite coefficients right here. You had 3y and negative 3y. When you add those together, what happens? They cancel out and go away, so you're left with something x equals a constant. That means you can immediately solve for x. Connor, yes?
And then
So here's the thing. That one right there automatically was a really nice candidate for elimination because, Nick, just chill for 1 sec, because you had opposite coefficients. Are you always going to have opposite coefficients? Sometimes you're going to be really close to it and you can make it happen. So here's an example right here. Do you see opposite coefficients right here?
yeah,
What is the coefficient of x in the first one? 5. What's the coefficient of x in the second one? 2. The coefficient of y in the first equation is negative 2. And what's the coefficient of y in the second equation? 3 is the coefficient of y. You have 5 and 2, negative 2 and 3. Are any of those opposites of one another? Meaning, are the coefficients of x obs the same as, are they opposites of one another?
Yeah.
5 and 2 are opposites of one another? No. What about negative 2 and 3? Are they opposite of one another? No, they are not. They are not. Am I allowed, if I wanted to, could I multiply this by 2 if I wanted to? As long as I multiply everything by 2, is that okay?
Yes.
Yes, it is. If I multiply everything by 2, Connor, can you tell me what it becomes?
10x minus 10y.
Nope. Try again. 10x
10x
minus,
8.
nope.
I mean 4. Sorry.
Thank
4
you.
y
Equals,
8.
correct. If I wanted to, Summer, could I multiply the bottom one by 5?
Yeah.
If I wanted to, could I multiply by 5? Yeah, I could. Now, Summer, can you tell me what I get?
10x plus 15y equals
65. Are any of those coefficient pairs opposites? Is 10 the opposite of 10? No. Is negative 4 the opposite of 15? No. So we almost got there. How were we almost close? Were we pretty close on one of them? We have 10 and 10. Is that pretty close?
Yeah.
We want one of those 10s to be a negative 10. Well, what can we do? Multiplied by a negative 1. What's it going to become? Negative 10x plus or minus what? 15y negative 65. Now what can we do with these two equations? Add them. What's 10x minus 10x? What's negative 4y minus 15y? 19y. And then here's another one for you kids. What's 8 minus 65? Negative 50 what?
8.
Negative 50 what? Is it negative 57?
Yes.
Yeah. So y is equal to negative 57 over negative 19. Anybody know what that is? That's 3.
Oh.
Cool. So now that we have y equals 3, what do we do with the y equals 3? This is important. You're going to do this a lot. Where do you plug it in? One of the first ones. Plug in, what was it, 3? So 5x minus 6 is equal to 4. 5x equals 10. So what does x equal? 2. So our answer would be 2, 3. What would be the last thing we would need to do? We're not going to do that right now, but you would need to check. You could do the other one. You should get the same answer. Yes, either one. Summer than Mar.
Why would
Of these two. So do you want to use substitution or elimination? What do you want to use? Let's use elimination. If we multiply this top one by 3, you get what? 6x minus 3y is equal to 9. Oh, they're the same. So if we subtract them, what do you end up with? If you subtract the same thing from itself, what do you get? 0 equals 0. That means it's the same line. We already knew it because we saw it. But if you end up with 7 equals 7, how many solutions does the equation have? The system, an infinite number. What happens if we did some work, though, like this one? See that one right there? Let's use substitution. Nick, what variable in the first equation should we solve for?
X.
Yeah. What is x going to equal, Nick? 4 minus 3y. X equals 4 minus 3y. You subtract 3y from both sides. What do we do, Shane, when we have x equals 4y? What do we do with that? We plug it in for x in which equation? The first or second? So that one to there, and then we plug it in right there. Negative 2 times 4 minus 3y minus 6y equals 3. One word for what we do next. Negative 8 plus 6y minus 6y equals... What's 6y minus 6y?
0.
Negative 8, 3. Is that true?
no?
Not true. So what does this mean? Parallel lines.
So
Which means how many solutions are there? No solutions. So if you're doing algebra and all of your algebra is correct and you end up with 2 equals 2, how many solutions do you have? Infinite number. If you do all of your algebra correctly and you get 6 equals 9, how many solutions are there? None. None. So if you get something that's untrue, no solutions. If you get something that's always true, it means an infinite number of solutions because it's the same line.